sound great, keys to successful voice management systems in game audio. I'm Will Augar. I'm the principal audio programmer at Frontier Developments. Here's a selection of our current games. So we've got Elite Dangerous, where you ride a spaceship and explore the galaxy. We've got Planet Coaster, where you build a theme park, fill it with roller coasters. Jurassic World Evolution, where you breed dinosaurs and then attempt to look after them in a Jurassic Park. See how that goes. And Planet Zoo, which came out a few weeks ago. This is our latest title, where you create a zoo, as the name suggests, and breed animals, look after the animals there. Okay, so here's a picture of us in our Cambridge office. This picture was taken about a year ago, so we've grown a little bit since then. So we're now up to 500 people in our Cambridge office. We're split between development and publishing, so we publish our own games. The audio team at Frontier, there's about 30 of us on the audio team now, and that's about 20 sound designers and about 10 kind of programmers and more technical people. Okay, so I'm basically just going to start with showing the Planet Zoo launch trailer because I think it's awesome and it's just got really cool music. Okay, there we have it. It's all about the red pandas. Okay. Okay, so here's just a quick overview of what we're going to be talking about today. We're going to be looking at the voice problem, what it is that we're wanting to manage with our voice systems. We're going to be having a look at the middleware solutions, some of their shortcomings, and we're going to have a sort of overview of how these the custom systems we've developed at Frontier have evolved over time, some of the lessons learned. And then really the main body of the talk is going to be on that last point, having a look at the latest voice management system, diving into some code, and hopefully giving you some food for thought there. Okay, so let's start with the voice problem. As I said, we've got a voice management system. There must be a problem. The problem is really when there are an excessive number of voices or sounds playing at any one time in the game. That's really problematic for us, and there are really problems in two areas. First is performance problems. Of course, voices use up CPU and memory for decode, for mixing, applying effects, things like that. In busy scenes, in busy open world environments, these can really ramp up. Performance becomes an issue. The other side is the aesthetic problems. Put simply, too many voices cause a muddy mix. So we'll lose detail. We might even miss important information for the player, stuff that they might be interested in. But generally, sound design are not going to be happy here. You know, the mix sounds muddy, things aren't great. We need to fix this. Okay, so as we come up with solutions to the problem, well, we need to evaluate them really. And the clue was in the name of the talk. We want them to run fast. That's have good performance characteristics. We want them to sound great, realize the sound design vision. But there's one other thing. The dev cost needs to be low. Now, we can't just spend, you know, a huge amount of time coming up with elaborate systems that take up all the programmer's time. We've got plenty of other things to be doing, and we'd really like to solve this and then move on to other things. Okay, so thinking about middleware. So actually, just before we get here, I was going to ask, actually, who here is in game audio? Either you work in game audio or you study it. Cool, good stuff. And just another one. Out of those people, how many people use WISE as part of the thing? It's everybody that put their hand up for the first question. So basically, WISE is kind of the standard, although we also have Fmod and various other things, various proprietary things. So WISE provides voice management. It's something that they provide in the box. It's important to them. And this is sort of set up by sound designers using the WISE authoring tool. So they'll basically set voice limits, they'll set behaviors, they'll set kind of budgets, this type of thing. They'll do it all in the WISE authoring tool. That's how WISE works. Okay, so middleware shortcomings. Now, I really want to stress this before I get into these points. Like, WISE is great. It's a fantastic tool. It's a brilliant sort of framework from a sort of runtime perspective, and the fact that it's cross-platform. The authoring tool it's basically the, you know, it's the DAW for interactive sound. You know, it's fantastic, but there are some problems with voice management. I'll just outline a few of them here. So in WISE, when voice count reaches a certain number, they start to virtualize voices, so just not play the audio. And virtual voice count can stack up, and that can actually start to degrade performance. Now, Audio Kinetic, who make WISE, say that if you have more than 1,000 game objects or like sound emitters in your scene, then you really need to start managing that count. You need some kind of like voice management system, effectively. So if you've got an open world game, you kind of need to be doing this. The second issue is the voice management is really interleaved with the sound design. So the sound designers are making this amazing interactive content, all their creativity is going in there. They're also kind of interleaving the voice management stuff. And that causes some real problems, actually. The third issue is at runtime, it's actually quite unclear how voices are being managed by WISE. It's quite hard to debug. So they do provide some profiling, some real-time profiling, but it's quite sort of mysterious as to actually what's going on with voices. Okay, so due to those shortcomings, at Frontier we thought, well, let's develop a custom solution to this. Like we need to do this. So we're going to address the shortcomings. We want to run faster, sound greater. Yeah, the dev cost. Yeah, that's going to be tough. Yeah, we'll try and find a way to deal with that. So the custom solutions, they're basically written on top of WISE. So we keep WISE. We use the Sound Engine API. We're dealing in emitters and events. We leave the individual sounds, behaviors, voices, we leave that to sound designers setting up in the authoring tool. We're basically managing emitters or audio objects and the events that we post through to WISE. Okay, so we're going to make a custom solution. Let's have a little think about requirements. So the classic approach to this in game audio is, let's just have the nearest 5, and we're done. Makes sense, right? They're the things that are right near the camera. We'll just play those. Voices are managed. Trouble is, in a complex game, particularly open world games, the requirements are sort of, you know, the kind of vision of the sound design team means that the requirements are significantly more complex. So I'll just run through a quick example of what those complex requirements might look like. So here's a kind of, here's a top-down view of a scene in Planet Zoo. As you can see, we've got a listener who's facing over and kind of watching, listening to the zebras in the habitat there. And if we just imagined a voice count of 5, nearest 5, then we just hear guests. But that's no good because like we really want to be hearing those zebras. Like we've put all this effort into making the zebras sound amazing. You know, the players should be interested in the zebras, want to hear zebras as well. Fine. We'll kind of take some of the guest emitters and we'll have like a couple of the zebras instead. And that works well. We've got some guests, some zebras. But then we've got an elephant who's like right over the other side of the park. Like he's way over the other end of the park. He trumpets or whatever, and well, we want to hear that. That's like an iconic sound. You know, that's going to be important. Can we hear him as well? Sure, okay, we'll kind of manage that somehow. Then we've got like, there's a lion, perhaps ill-advisedly, in the zebra habitat. And he's about to, he's going to start hunting the zebra. Okay, so this is like a kind of key point in the game. We want to hear him as well. He's not one of the nearest animals, and he's doing a specific behavior, so we only want to hear him when he's hunting. We want to hear the lion. There's a vet down at the bottom there. Well, she's basically having a look at our setup with the lions and the zebras and is saying, look, you shouldn't be doing this. And that's a key bit of player feedback, so we also want to hear her when she gives you that kind of that feedback. And we've also got some trees. It'd be nice to have some ambience, that type of thing. So let's hear some trees as well. So there's a whole bunch of requirements there, and I hope it's sort of clear that the priorities change, and it's not just like a one-size-fits-all thing. It's like a dynamically changing scene. We want the emitter management, the voice management to be dynamic too. Okay. So just a real quick history of voice management systems at Frontier. So back in the day, we didn't have a system, just some ad hoc code. That was not a great way of doing it. We sort of ran into problems. We had to put management in right at the end of, right near a release, and it was kind of a blunt tool. So the outcome, the learning point from that was we need a system. When Elite Dangerous was developed, the team developed some generic systems to deal with voice management, but the systems were quite brittle, so they solved the job, but then another scenario would come up that we needed to solve, so we had to write a new system. So we ended up having multiple systems, which wasn't great. So the learning point was we need to be able to customize. Planet Coaster, the team developed a really flexible system. They could add all the customizations they liked, ended up with a great sounding game, but it was a real dev cost coming up with all these custom systems. Each one was done differently, and you know, really the sort of learning point here was we need to find a way to reduce development costs. So that brings us on to the latest system, first used in Jurassic World Evolution. Since then, Planet Zoo has also used the same system, and beyond, so future projects, and also kind of backporting it to older projects. So the aims of the new system were to maintain, hopefully improve, the performance and aesthetic characteristics of the old systems, but to reduce dev costs. So how are we going to do that? Like, how can we possibly get here? So the idea is that we want to be as generic where possible, but allow customizations when needed. So that was kind of the key thing. So thinking about those aims, thinking about this idea of generic but customizable, we turned to some programming best practices. And these are very well known. I expect you've kind of heard of these, but these were kind of key in our thinking when we were designing the new system for Jurassic World and beyond. So the first is don't repeat yourself. If you write a piece of code that does a job, you don't want to rewrite that multiple times. It just doesn't make sense. It's difficult to optimize if you've repeated yourself. If you have bugs, well, you've suddenly got multiple places where you need to squash them. It's just not a great way of going. So the next kind of best practice is this idea of separation of concerns. So the idea is that each piece of code does exactly one job, and we kind of abstract those away from each other. Now this also really helps for optimization, because if each piece of code does one job, you can really kind of polish that, possibly add features, and you're not going to impact on other parts of the system. So don't repeat yourself. Separation of concerns. These were some things that we were considering. Okay, so let's start to have a look at the current system. So this is just an overview, really, of how the voice management system fits in to the other parts of the game. So on the far left, we've got game data. Could be anything. Animations, game state. A million and one things there. We've got audio triggering. We want to trigger audio based off that game data. Then we're going to feed into the voice management system, which is going to try and, as the name suggests, it's going to control the number of emitters, really, number of audio objects. And then we kind of pass that through to Wise, to the sound engine, and that's going to actually render those sounds, position things spatially, do that type of thing. But we're going to be looking really at that voice management block. So, some of the key concepts of our system. Okay, so the first is categories. So simply by splitting up the emitters into discrete categories, so we might have animals from our scene before, people, environment, so distinct categories. This lets us kind of consider the behavior for this one category, and it doesn't we don't have to manage multiple categories at once. We can just focus on one thing, get that right. Then we have budgets. We want them to be clear. We want it to be really obvious exactly how many animal emitters we can have at once. We want the budgets to be flexible. Like we want iteration, and we want to tune that so it's just right. But we do want them to be strictly enforced. We don't want there to be any way that the budget can be exceeded in our system. That helps. So the third thing is this idea of recipes. So we've got our budgets, but then how do we pick which emitters should play? Now recipes can be super generic, like saying, well, we just want the nearest to the camera. But they also allow contextual customization. So if we think about, we want to hear the lion when he's hunting, that type of context-specific stuff. So we want the recipes to be customizable when they need to be. Okay, so this is a kind of overview of the voice management part of the diagram that we looked at before. I'm going to keep bringing this diagram up, so don't worry if if you don't take it all in the first time. But basically, we're going to go from audio triggering through to dynamic objects. We've got a virtualizer that will kind of switch things on and off, allow things through to the sound engine or not. And we've got budgets and recipes that are influencing what actually gets switched on, what gets switched off. Okay, so I'm going to show you some code. It's slide code. It's sort of designed to fit on the slide. Probably you wouldn't want to use this code exactly for production, but hopefully it does provide you some food for thought and maybe something that you can build into your own systems. Okay, so first up, we're going to talk about audio objects. These are the kind of core components of the system that allow us to manage voices. So first up, we've got the concept of a physical audio object. This is something that, that holds a WISE registered object. So when you register an object with WISE, it allows you to then position that object, to post events to it, etc. Physical audio object provides an API to make sound engine calls. So in WISE, we can do things like post event. And this object uses the RAII principle. So we register the game object in the constructor, and when the object gets destroyed, it automatically cleans up. That's handy. If you're not using any sort of voice management system, then I suggest that a class like this could be all you need. So let's have a quick look at what that might look like. So here's our physical audio object class. The constructor takes a name. It has a destructor, as we're doing RAII. We're deleting copy. We're enabling move. It doesn't make sense to make copies of this object. It's wrapping a resource. We've got, yeah, as you can see, post event, set transform. In reality, you'd have a bunch of different API calls that are kind of getting through to the sound engine. And the data we have is just simply the ID. That's all we need to store. So have a quick look at some implementation details. So the constructor will basically have a mechanism for creating an ID. We'll register ourselves with the sound engine. Nice and simple. We'll post event, which we'll use the event and the ID that we created and kind of pipe that through to the sound engine API. And in the destructor, we'll unregister the game object with WISE, make sure we don't leave any loose ends. Okay, so next up, we're going to look at the concept of a virtual audio object. So rather than posting events through to WISE, this guy is going to cache events and positions. It's going to provide a mechanism for retrieving data. So we're going to ask which events have we virtually posted, that type of thing. So here's our virtual audio object class. It's kind of similar to the physical audio object. This time we've got an update function, and we've got the get name, get events, like a mechanism for like retrieving the events that it's cached. I've just defined a quick event struct on the right there. So we store things like name, time elapsed, the duration, these type of things. And we've just got a vector of events, which is going to be our container for storing the cached events, as you can see there. So how does that look like from an implementation point of view? So post-event, we simply grab some metadata. That's just data from the sound bank that will tell us if it's looping, things like that, the duration. And then we just place that in our vector. We've cached it. Nice and simple. In update, we want to kind of update the elapsed time on all of our events, all of the events in our container, so we can basically find out if the elapsed time has exceeded the duration. Then we'll just get rid of the event. It means that event has been virtualized for too long. It's basically the sound has finished playing, so we'll just remove that event. Okay, so we've talked about physical audio objects, virtual audio objects. The dynamic audio object basically holds, it's composed of a physical audio object and a virtual audio object, and it switches between physical and virtual. It forwards API calls, such as post event, set position. It forwards those to either the physical or the virtual. So it kind of looks a bit like this. So we've got, on the left, we've got a physical dynamic audio object. It's got its physical, it's got its virtual. We then kind of virtualize it, moving over to the right. The physical audio object, we just destroy that. It tidies everything up with WISE. but we've still got the virtual audio object with all our cached events. And then we can move from virtual back to physical, bring everything back to life, should we wish to. So let's have a quick look at dynamic audio object, a sort of familiar public API with post event set transform. It's also got these physicalize and virtualize member functions in its public API. Now they basically let the outside world, as the name suggests, physicalize, so it's posting events through to Wise, or virtualize, so it's just caching events. And you can see there in the members, it's got an optional physical audio object that's going to either be there or not, and it's got a virtual audio object. And you can see there I've kind of made the constructor private and used a mechanism to allow a dynamic audio object creator to construct these things. That's just so we can keep track of who's actually making these guys. And in reality, the physicalize and virtualize, they'd be kind of hidden away. They wouldn't be public like that, but just for simplicity, they're there. But basically, a particular type's job is going to be to calling those functions. Okay, so this is what physicalize might look like for a dynamic audio object. If we're already physical, nothing to see here, just return out. Otherwise, we'll make a physical audio object and we'll cycle through all of the events that our virtual audio object has cached, and we'll basically, we'll physicalize them. We'll post the event through to Wise. We'll set a position with the time elapsed. It will kind of bring back to life those events. When we virtualize, we simply reset our optional, destroying the physical audio object. The cleanup happens automatically. Nice and straightforward. So that's our audio object story. Those three guys there. Okay. Next up, we're going to look at how we actually deal with budgets. How we kind of decide, well, how many of these things are we actually going to allow to be physical at any one point? So yeah, budgets specify the maximum number of physical audio objects per category. So maybe animals, maybe people, maybe trees. The categories are project specific, whatever makes sense to you. We find that too many categories can get confusing. You might want to just rein that in a little bit. And real-time control of the budget is super useful for just getting the right sweet spot. Good for iteration. So if your engine provides a mechanism for changing a resource in real time, lovely, that's going to be helpful. So a budget's pretty straightforward. Let's just call it a map of string to int. When we create budget, we just say, yeah, animals 3, people 7. That's our budget. So the chancellor is the type that distributes the budget between the categories. So it's important to get this bit right because you don't really want to have more physical audio objects than your budget suggests. So the chancellor, very strict, never overspends. There's all sorts of different ways to hook this up, depending on your game engine. It's also possible to have multiple budgets. If you need a budget for one part of the game, a budget for another part, you can potentially write a chancellor that transitions between budgets. So chancellor simply creates a budget and then provides access to it. It's just hooked up in whichever way works for you. Okay, so working our way through our diagram, we're now going to look at the virtualizer. So the virtualizer is the bit in the middle there. It basically decides whether the dynamic audio objects should be posting stuff through to Wise or not. So yeah, it takes its budget from the Chancellor. It kind of uses the recipe to basically, well, the recipe will basically assign priorities to the audio objects, associate a priority with each audio object. The virtualizer is just going to say, okay, I want the highest priority, you know, say 4 to be physical. So yeah, so on the left, I'm just showing a struct called dynamic audio data. It's got a dynamic audio object in there. It's also got a priority, which is how the virtualizer is going to decide which things should be physical. We've also got an entity ID in there that just helps kind of associate the audio object with other with entities in the game. And we'll sort of have a sorting operator, a less than operator that we're going to use to sort our dynamic audio objects. That's just going to compare the priority between any two objects. And for the sake of simplicity, we'll just create an alias called dynamic audio. It's a vector of that dynamic audio data. So, virtualizer, it's going to be given a budget, and then it's got an update where it's just going to iterate through a container of dynamic audio. And inside its update, it will look something like this. So it will basically sort the audio objects first in priority. It will then count through them, and when the physical count exceeds its budget, it will basically start virtualizing them. So you can see there. So as it's counting up, make sure they're physical. When we exceed the number, it's time to start virtualizing the audio objects. Okay, so now we're going to look at basically the part of the system where all the customization happens, and that's in the recipe. So far, that's just like a generic approach that we can apply to everything, but the recipes do want to be different. So it's an algorithm that determines the priority of each dynamic audio object. As I said, these can be generic, like distance to listener is visible, something like that. You can kind of compose recipes. I'll show you a little example of that. And we really want to write the customizable, super specific things when we need to do that for stuff like the lion hunting. So this is what a distance recipe might look like. So we take a transform manager, which is just some other class that deals with the transforms of all the objects in the world, and we have an apply function. Inside the apply, we will loop through all the dynamic audio, and we'll grab the distance to listener from the transform manager, and we'll just take that as the priority. So things that are really close to the camera, close to the listener, they have a really small distance to listener, so a really low priority value, but a low priority value means it's very important, if that makes sense. So as things get further away, the priority value sort of increases. They're less important. They're further away from the listener. Okay, so that's what a recipe might look like. Distance to listener, feed into the virtualizer, and we'll decide which things to switch on and off. So that's quite a lot of things. It sounds like we need a manager. Yes, I knew there was going to be a manager. Here it is. So basically this class, instances of this class will basically manage that whole dance between all the things that we talked about. It's worth stressing here that you would have a manager like this per category of sound. So you'd have a manager for your animals, you'd have a manager for your people, for your guests, or whatever other category makes sense to you. And yeah, it's dealing with the object, the budget, the recipe, the virtualizer. It can also deal with like other things that make sense. Like you might want to have the manager post the transforms for each object through to Wise. That's quite handy. You might want to do send distance to listener through as an RTPC. You might want to do obstruction. There's a whole bunch of things here that you can have the manager do. So yeah, that's the manager. So you can just see here, it's just an object that allows you to create audio handles to actually get these things out to post events on. But then it just contains the recipe, the virtualizer. It has the dynamic audio, which is, if you remember, our container of objects and priorities. And that's the manager. So a quick look at some implementation for the manager. We might want to create audio handles. We'll just make a shared pointer of a dynamic audio object, fill it with the data it needs, and return that out to clients. When the clients drop their audio handle, we'll also need a sort of mechanism to notice that that's happened and clean up the object in our container, but that's just sort of outside of the scope of this talk. Update, we're just going to apply the recipe, run the virtualizer, do other things like setting transforms. That's where all that good stuff is going to happen. Okay, so far we've been quite generic. We've talked about customizing. Let's solve this with templates, of course. So the Dynamic Object Manager gets a recipe template parameter. So let's think of the example of a visibility, a visible recipe. Let's see what that would look like. So a visible recipe, it's kind of similar to distance to listener, but it takes a visibility manager. And you can see, that can just tell us if things are visible or not. That can be calculated off to the side in a nice performant fashion. And we're also going to compose in a distance recipe into the visibility recipe. So first off, we run the distance recipe. We essentially assign priorities to everything based on distance to listener. Then we sort them. So we've got our closest things first. And then we just run through, and if the visibility manager says it's not visible, we force the priority to lowest. So that will basically leave us with a set of dynamic audio that has the nearest things, higher priority, and anything that's invisible, like behind the camera, just at the bottom of the list. And here's our audio object manager, this time with the recipe template param, and we can see at the bottom we would just declare a audio object manager with the visible recipe. So that's fine, but now we want more game-specific customizations, so of course more templates. Clients can basically specify, they're going to need to specify arbitrary data for these recipes to run with. So let's have a look at what that might be. So an animal recipe. At the top there, we've extended the regular dynamic audio data that had the object and the priority, if you remember. It's now got an animal type. The animal recipe looks, I guess, fairly familiar. It contains a distance recipe. We've got a reference to the animal manager to ask it things. And inside the body of the recipe, we'll run the distance recipe, we'll sort it. So we've got our audio handles sorted by distance to listener. And then we'll go through, and in this recipe, we'll count the zebras. And when we have more than 10 zebras, we'll just start virtualizing those zebras. Because in this case, yeah, we had a problem with there being far too many zebra emitters. So this would be a way to solve that. So our audio object manager starting to get a little bit templatey now, but we've basically got a recipe template param and a dynamic data param. The class is the same apart from that. And you can see how you would declare an object manager with animal recipe, animal data. I guess that's relatively straightforward. Yeah, so there we have it. That's a kind of whistle-stop tour of the different classes that you might make up a voice management system with. So hooking into the game. So I think the key idea here is that when your data retrieval gets complex, so like when you've got a lot of different managers, there's a lot going on in the game, and when your emitter code, your audio handle code, when that gets complex, like you might have multiple emitters on each entity in the game or something like that, then it makes a lot of sense to keep things apart, to keep your data retrieval and your handle code separate. So I'd like to recommend a sort of simple declarative style API, keep the management of audio handles encapsulated. Of course, the voice management stuff, that's all in that system, so you're not going to be crossing your wires there. So how might that look? So here's a simple tree audio class. So when we add tree, we just create a handle called tree, post a tree loop, store the handle. Nice and simple. When we do remove tree, we just drop the handle. And that's really all that happens in that simple case. Guest audio, we have the same kind of create the handle. This time we're not going to post event immediately because up in the top right, on guest cheer might come from an animation system. It will be actually posting the cheers there. We simply retrieve our handle that we need, post the event on it, and that's fine. And in terms of voice management, all we do is we just have a manager as our private member. That's all of the voice management stuff happens automatically. Yeah, I should note when you have, we had some default parameter, template parameters. So if you don't specify anything, it will just do distance to listener, just the most basic thing. Okay, so animals, we're just going to add them, remove them in the same way. Yeah, the call from on animal call will come from an animation system where we just post the event. And you can see here we're just saying, okay, we want the animal recipe here. And that's got all that stuff. So that's really some examples of us using the system. I'm just going to show a capture that just shows from a debug build of Planet Zoo that just shows the emitter system in action, and it basically debug renders the physical and the virtual events. Sorry, the emitters. So let's have a little look at this. It's from a debug build, so you'll have to excuse the frame rate. So these are like all the emitters in the scene. I just filtered animals and crowd. Get all the detail popping in there when you're really close to the elephant, and now it's virtualized some of that. Okay, so that's a little look at some of the system in action. I think I've burnt through almost all my time, so I'm going to be quite quick here. Evaluation of the system, well, the audio render was significantly down. The CPU of this system is actually reasonable with the optimizations we were able to do because we split things up. I think the games have a real aesthetic focus to the voice management. We're allowed quite a dynamic mix, something that's quite responsive to the context in the game. Development cost, initially it was like basically a year. We've made significant changes to it since then, but most importantly, we've been able to reuse and kind of port it back. So I think we've kind of achieved on the development cost side. So just to run down a recap, voice management system is key to good sounding games. Although middleware solutions can be problematic, custom voice management can address this. Development of custom voice management systems is really helped by best practice, separation of concerns, don't repeat yourself. And custom VMS definitely makes sense if you can reuse that tech. And that's the end of the talk, so I'd like to thank you for your time. Basically, if anybody comes up with other questions, just come and find me at the conference. Just come and speak to me about it, but sure.
Yeah, just for interest, how's the rate of updates, which sound you may hear or not, so depending to the position?
So we update the position of all the objects once per frame, and the game runs at 30 frames a second. So.
Okay, quite often.
But yeah, if you have anything else, please come and find me and speak to me. I'd be happy to speak to you about it. Thank you.